Today's lecture comes from Chapter 6. We're going to talk about stability and cloud development. This chapter in particular, we will look at definitions and causes of stable and unstable atmospheric air. We'll also talk about the processes that cause instability and cloud development. The question may come to you, why are we even concerning ourselves with stability and cloud development? Well, one of the first things that we notice are clouds are beautiful. They come in many shapes, sizes, and often people will actually look at clouds and begin to imagine figures and characters from looking at clouds. One of my major professors when I was at Iowa State, Dr. Richard Carlson, actually found the Energizer Bunny in one of the clouds. So there's a lot of fun there. As we've talked about in previous modules, developing clouds release a tremendous amount of energy into the atmosphere in the form of latent heat release. Clouds, as we also learned from Chapter 2, help to regulate the Earth's energy balance by reflecting and scattering shortwave radiation back into space, and the long-wave radiation that's emitted from the Earth is often absorbed and emitted by the clouds to help keep us warmer than if we did not have clouds. And in terms of forecasting, clouds are often an important signpost for impending events that will occur in the weather in the future. And so with forecasting being a tremendously important part of this class, being able to look at clouds will help you to infer the weather over the next couple of days. So the first question that we'll ask is, how do clouds form? Well, if you recall from Mountain Sim, we took a parcel of air, which was represented by that leaf. We moved it up the mountain. We noticed that it began to cool, and as it reached the saturation vapor pressure curve, it began to condense, and a cloud was formed. Well, two things that you need to have to form a cloud. Obviously, you need to have sufficient moisture present in the atmosphere. And then we need a way to actually move air upward through the atmosphere to where it eventually cools and condenses. In this particular chapter, we will learn why air sometimes rises and sometimes sinks or is stationary in the atmosphere. Before we begin today's discussion, I would just like to focus on an air parcel. Now, we've talked about this previously in class when we were talking about the molecular makeup of a piece of air. We know that approximately 79% of a parcel of air is made up of nitrogen, and about 20% oxygen, and then water vapor being a variable gas in this particular area. Now, what I would like you to do is to keep in mind that this parcel of air is going to be separate from the rest of the atmosphere. In a way, you can think of it as being insulated from the air surrounding it. In other words, there's no exchange of heat or molecules from within the air parcel to the air outside of the air parcel. So we're just going to look at this air parcel as a bubble of air that is insulated from the rest of the atmosphere. Now, as we begin to move this air parcel up and down, basically, as we learned from Chapter 1, that the density of the atmosphere decreases as we head upward through the atmosphere. So as we move this air parcel up to an area of decreased density, the air parcel will begin to expand. So we look at this air parcel here, and as this air parcel begins to move up in the atmosphere, it will begin to expand, and we'll talk about how it expands and why it expands. And then as this air parcel begins to move downward, it will compress or shrink. Now let's talk about the air parcel for a moment. Let me just go ahead and draw on the screen here the ground, and let's say we have this bubble of air. And we begin to move it upward through the atmosphere. As we begin to move it upward, the molecules inside of this air parcel, made up of nitrogen, oxygen, water vapor, and other constituent gases, what will end up happening as the air parcel begins to move upward, where it is less dense, the molecules begin to do work on the inside of this air bubble. In other words, it begins to expend energy to push outward on this parcel of air. and so the parcel of air begins to get larger. Now keep in mind, it uses some of its internal energy to do this work, to expend energy. To be able to increase the size of the air parcel, molecules have to do work, and it does work against the surrounding atmosphere. We all know that when we begin to expend energy, the molecular motion, the average molecular motion inside the air parcel begins to decrease. And we know that temperature is related to the average molecular speed. And so as the molecules begin to expend energy to increase the size of this air parcel, the average speed begins to decrease, and so we would see temperature also beginning to decrease. Now we'll take the other case where we take the air parcel, and again the surface I'm drawing right here, and we begin to move this air parcel down. As we begin to move the air parcel downward, the density of the atmosphere increases, and now the atmosphere is actually doing work on the air parcel. And so it begins to compress the air parcel. And so since the atmosphere is doing work on the air parcel, the average molecular speed begins to increase inside the air parcel. And so we know that temperature would begin to increase. So when we raise an air parcel up, it expands and cools. And when we take an air parcel and we begin to have it descend throughout the atmosphere, it compresses and warms. And running Mountain Sim, you should have seen this. And if you haven't, if you can't recall this, I would encourage you to go to Mountain Sim and actually run the simulation again. Now there's some terminology related to the concept of an air parcel. One of the terms that we will use is called adiabatic process. We've actually identified what this is in the last two slides. The adiabatic process means that there is no exchange of heat with the surroundings. So the air parcel, we talk about it being insulated. There is no exchange of energy from within or outside of the air parcel. We also have a few ways to describe the warming and cooling of an air parcel. Now, recall that we talked about taking an air parcel from the surface and moving it up through the atmosphere. And we know that basically the air parcel begins to cool because the average molecular speed begins to decrease because the air parcel is doing work against the atmosphere. It's actually pushing out on the sides of the air parcel to expand it. So it cools. And again, recall that as the air begins to descend, it begins to compress and warm. Well, we can actually describe this warming and cooling in two terms. If the air parcel is considered dry, in other words, unsaturated, we'll call this cooling or warming by the dry adiabatic lapse rate. However, if the parcel is saturated, and recall that the parcel reached saturation in Mountain Sim when it hit the saturation vapor pressure curve. Recall that when it hit the curve, we actually had condensation and the cloud formed. At that point, any change in temperature would be the moist adiabatic lapse rate. You see the rate of heating or cooling is about 10 degrees Celsius per 1 kilometer for the dry adiabatic lapse rate. And we'll give specific examples on that in just a moment. But recall that a lapse rate is just how temperature increases or decreases in the atmosphere. So again, the two terms, dry adiabatic lapse rate, temperature changes, either warms or cools 10 degrees Celsius per every 1 kilometer it travels up or down in the atmosphere. And if the parcel is saturated, then it would change at the rate of about 6 degrees Celsius per kilometer. I should mention, though, however, that the moist adiabatic lapse rate is highly variable, and it depends upon the temperature and moisture content of the air parcel. But for what we're going to be doing in Chapter 6, we'll consider this change to be about 6 degrees Celsius per 1 kilometer. Now, this part right here, if you understand what I'm about to talk about here in the next few minutes, this chapter will get to be quite easy for you. And you'll probably have to review this particular part of the module several times before the concepts stick. But what we're going to do is we're going to take this air parcel here, and we're going to constantly compare the temperature of the air parcel to the temperature of the surrounding atmosphere. Okay, recall that this is an adiabatic process, so there's no exchange of energy between the atmosphere and the air parcel itself, which is shown here. So what we'll do, we'll continually compare the temperature of the air parcel to the temperature of the surrounding atmosphere, and you'll see why here in just a few moments. Basically, the reason why we want to compare the temperature of the air parcel to the rest of the atmosphere is we want to see if this air parcel will either rise or fall or stay in its current position in the atmosphere. If the air parcel temperature itself is warmer than the surrounding air, then the parcel will continue to rise. And you all are familiar with this. If you've ever been up to your attic during a hot summer day, you notice that it's hotter in the attic than it is down in the basement. Warm air begins to rise because it's more buoyant, less dense. And so, again, if the air parcel itself is warmer than the surrounding atmosphere, it will continue to rise. Conversely, if the air parcel's temperature is colder than the surrounding atmosphere, it will fall. Warm air being heavier, or cold air being heavier, more dense. If the temperature of the air parcel and the atmosphere is the same, the air parcel will stay at its current position. So you might be asking yourself at this point, why do I even care whether the air parcel is rising or sinking? Well, do you recall Mountain Sim? Let me just go ahead and run Mountain Sim here just a moment. Okay, let's run Mountain Sim. Now you'll notice as the leaf, which basically represents the air parcel, as it moved up the mountain, it began to expand and cool. You can't actually see the expansion, but you could see the cooling that took place as we started off here at the surface, and we began to move up in the atmosphere. This is altitude, temperature, and we saw that temperature initially was right around 25, and temperature began to decrease. And let's just go ahead and run it again. Again, the temperature starting at 25 here. And you see the temperature decreasing, and the temperature is decreasing simply because the parcel is doing work against the atmosphere. And you'll probably notice that once it reached saturation, it hit the saturation vapor pressure curve, we actually had the formation of a cloud, and you see some precipitation. In Chapter 7, we'll learn about precipitation processes. Okay, now that you understand or have a pretty decent idea about the air parcel versus the rest of the atmosphere, let's actually get into stability and movement. Here's an example that I've used in many previous classes before. You actually have someone sitting down here in a valley, sitting on a rock, and this person begins to move the rock up the hill, and all of a sudden the rock begins to fall back down toward the valley. This is what we would call stable equilibrium, where we attempt to move the rock up the mountain, but it wants to return back to where it started. This is what we would determine as a stable situation. In other words, the rock comes back to where it began. In the other area, which we call unstable equilibrium, we displace the rock down the hill, and you see here it begins to move down the hill, and it does not return to the top of the hill. It goes down into the valley. This is what we call unstable. So basically we give a push to the rock, and it moves away from its original location, does not return. So that's really the difference between stability and instability, is that we begin to move the rock away, and if it returns to its original location, we consider that stable. If we push it and it moves away from its original location, not coming back, we consider that unstable. Well, we can do the same thing with a piece of air, with an air parcel. Again, we call, for instance, we have this air parcel sitting here. It's at 30 degrees Celsius, and as it begins to go up into the atmosphere, notice that after it gets to 1 kilometer, 1,000 meters equals 1 kilometer. Do you recall how we talked about how the temperature of the air parcel would change so many degrees per kilometer if the air parcel was considered unsaturated? In other words, not saturated, it's considered dry. It changes at 10 degrees Celsius per 1 kilometer, or 1,000 meters, however you want to look at this. And we see that as it went from the surface up to 1,000 meters, or 1 kilometer, it went from 30 to 20. And of course it changed its temperature because of the work it's doing against the atmosphere as it begins to expend some of its energy. If we raise it another kilometer, or another 1,000 meters, up to 2,000, it decreases down to 10. It becomes even larger. So again, the rising air expands, it uses its energy to push out, which slows the molecular speed inside the air parcel, and so it cools. We're not bringing in cooler air from the outside, we're not losing air from inside the parcel because we said it's adiabatic. There is no exchange of energy between the surrounding atmosphere and the air parcel. The change in temperature is based upon the expenditure of energy by the air parcel. Now the parcel of air may be forced to rise or sink, and what we'll do is we'll compare the temperature of the air parcel with the temperature of the surrounding atmosphere to see if it will actually rise or sink, if it's considered stable or unstable. In this particular case, in this example we used, we push the parcel up and it continues to move upward. We would consider this an unstable atmosphere. Now, the graphs that you're looking at here, there's a lot of information, so I'm going to spend a little time to basically explain what is going on here. It's critical at this point that you understand what's going on here. Now, one of the things that we're looking at, the y-axis that I'm pointing out here, is altitude, and we've got it in meters. I really tend to like to use kilometers, so I'm going to make this 1 kilometer. 1,000 meters equals 1 kilometer. This is 2 kilometers, which is about a little over a mile up in the atmosphere. And then we've got 3 kilometers, which is almost 2 miles up in the atmosphere. So what we're doing is we're going to look at height, a vertical height in the atmosphere, and then temperature. Temperature going from 0 Celsius to 30 Celsius. And again, we look at dry and moist adiabatic rates. The dry adiabatic rate, the change of temperature of an air parcel, if it's dry, is 10 degrees Celsius per 1 kilometer. The air parcel's moist adiabatic rate, in other words, if the parcel is saturated, it changes at a rate of 6 degrees Celsius per 1 kilometer. Now, what we're looking at here, this helicopter, this helicopter, it represents a piece of air in the atmosphere, the artist's rendition here. And notice the temperature of the air parcel at the surface is 30 degrees. As we go up 1 kilometer, the temperature of the air parcel, since it's dry, changes by 10 degrees Celsius per every kilometer. So now it's 20. It goes up 1 more kilometer, and so it decreases to 10 kilometers. Notice the size of the parcel is getting larger. The density of the atmosphere around it's getting less, and so the parcel is expending its energy. It's using energy to make itself larger. And if it goes up to 3 kilometers, it changes down to 0. So as the balloon, or this air parcel, went from the surface up to 3 kilometers, the temperature decreased by 30 degrees. In other words, it changed by 10 degrees Celsius per kilometer. And what that is, it's represented here graphically as the dry adiabatic rate. This is a line that went from 30 degrees Celsius at the surface and going all the way up to 3 kilometers goes to 0. So if I were to go here at 2 kilometers and look down, the temperature here would be 10. If I go to 1 kilometer and look down, the temperature would be 20. So this line represents the rate of change of temperature of the air parcel, and it decreases at 10 degrees Celsius per kilometer. Now this other line is also a temperature change, but it's the temperature change of the atmosphere, not the air parcel. The air parcel's change in temperature is represented by the dry adiabatic lapse rate that I'm pointing out right here. The change in the atmosphere, the surrounding atmosphere, is represented by this, what we call an environmental lapse rate. Notice that if we go from the surface, 30 degrees Celsius of the atmosphere, we go up to 1 kilometer, the temperature is about 26 degrees Celsius. So the temperature of the atmosphere is changing 4 degrees Celsius per 1,000 meters or 1 kilometer. Now just take a few moments just to kind of get that straight in your head. We're looking at the change in temperature of the air parcel, and it changes at the dry adiabatic rate, and then we're looking at the change in temperature of the surrounding atmosphere, which is at 4 degrees Celsius per kilometer. So now let's compare the temperature of the air parcel at the surface is 30. The temperature of the surrounding atmosphere is also 30. Well, let's say that we take this helicopter, takes this piece of air up to 1 meter or 1 kilometer. The temperature of the air parcel is 20 because it's changed by 10 degrees Celsius per kilometer. However, the temperature of the surrounding atmosphere is 26. So now we see that the air parcel is colder than the surrounding atmosphere. Think about it. The air parcel is colder than the surrounding atmosphere. So, the question posed here, will this air parcel continue to rise on its own, or will it sink back down to the surface? Well, we know that the parcel at 20 is 6 degrees colder than the surrounding atmosphere, so the air parcel is colder. It's going to be more dense, heavier. It will want to sink back down to its original position. So we would say that this air parcel is sitting in a stable environment. Recall the previous slide. We talked about stability and instability. We push this rock up, and it wants to return to its original position down here. Well, it's the same thing. This air parcel is colder than the surrounding atmosphere, and so it wants to sink back to its original position. Now, let's say, for instance, that the air parcel is saturated. This same air parcel starting at 30 degrees Celsius, and since it's saturated, or since it's considered moist, it will change temperature at the moist adiabatic rate of 6 degrees Celsius per kilometer. Again, when we talk about the dry and the moist adiabatic rates, we're talking about the temperature change of the air parcel. And so now the air parcel at 1 kilometer, we go down here, it's about 24 degrees Celsius. And so we see that the air parcel is 24. However, the surrounding atmosphere continues to change at 4 degrees Celsius per kilometer. So at 1 kilometer, if I look at the temperature here is about 26 of the surrounding atmosphere. The air parcel is still colder than the surrounding atmosphere. And so this air parcel, left on its own, would sink straight back down. So think about it. Because the environmental air cools more slowly, the parcel of air held by the helicopter is always cooler and so wants to sink back to its original position. This is what we would term a stable atmospheric condition. Cold air, and this type of situation occurs in the atmosphere when you have cold air sitting below warm air. If we go back to RADSIM, look at this situation. This was over sand at night. We see that temperature at the surface was about 39, but as we go up into the atmosphere, we see that temperature is increasing. And in fact, at about 401 meters, the actual temperature is about 44, but at the surface, it's 39. And so we have a situation here where we have cold air at the surface sitting below warm air aloft, or about 400 meters up. Whenever we have warm air sitting over cold air, this is considered a stable condition because cold air has a higher density, and when we begin to move it, it will want to move back down toward the surface. Typically, your morning atmosphere has this type of vertical profile, and this is a condition that we call absolutely unstable. In other words, the environmental lapse rate, the change in temperature of the atmosphere, is less than the change in temperature of a moist air parcel. So absolute stability is when the environmental lapse rate, in our previous example, was 4 degrees Celsius per kilometer, and the rate of change in temperature of the parcel was 6 degrees Celsius per 1 kilometer. This type of situation we would see stable conditions. In other words, nice weather. And again, here we've got a situation that we're terming absolutely stable. Let's look at this. Again, the temperature of the environment changes 4 degrees Celsius per kilometer. The change in temperature of the air parcel is at 10 degrees Celsius per kilometer. So the air parcel of dry air, right here, at 20, is colder than the surrounding atmosphere at 26. If we look at a moist air parcel, same thing. The moist air parcel is colder than the surrounding atmosphere, which is 26 in this case, and so it will want to sink back down. Now, clouds that can be produced in stable atmospheric conditions. Now, you'll recall earlier I mentioned that clouds can be a precursor of weather events. And so typically, if we're able to force absolutely stable air, in other words, in the example we used, we had a helicopter pulling that piece of air up into the atmosphere because on its own it would want to sink back down. But let's say we have air moving up over a mountain, like in Mountain Sim, or we have a front, a cold front or a warm front that's lifting the air. If it's lifting absolutely stable air, we'll see clouds such as cirrostratus clouds, altostratus, or stratus clouds, nimbostratus, those types of clouds. So if you see those types of clouds, you've got a stable atmosphere. Now, the question may come up, okay, how can we bring stable atmospheric conditions? How can that be produced? Recall that we said a stable atmosphere is when you have warmer air sitting on top of cooler air. For instance, the air here at about 401 meters is about 44, and the temperature at the surface is about 39. Well, there's several ways that we can do this. We can bring warm air advection. Recall advection is horizontal movement of air. We can bring warm air into an area aloft, let's say at about 2 miles up or about a mile up. In this particular case, we have a map here, and this is pretty messy, but the colors correspond to temperatures. And let's look at this area over here in the Pacific Northwest. This is the western coast of the U.S. And what we're seeing is we're seeing warmer air coming in from the Pacific. And this is occurring at 850 millibars, which is about a mile up from the surface. And so that's one way. We can bring warmer air aloft. We'll look at these types of maps in some of our labs. You'll learn how to use these maps pretty quickly. One other way is we can cool the surface. Let's say we don't warm the air above, but we cool the surface by radiational cooling. That's what's happening here. This is the daytime profile of temperature of sand, but as we go through the night, it begins to cool. So radiational cooling can produce stable atmosphere. Or we have cold air advection at the surface. We bring in cold air at the surface like we're experiencing these days here in Iowa. Or if we take an entire layer of the atmosphere and move it down, this will produce a stable condition. Now this may seem a bit strange. How do you take an entire layer and move it down, and how does that produce stable conditions? Well, now what you're looking at here is we have a graph of pressure in millibars. So the surface is right around 1,000 millibars. And as we go on up to about the halfway point, 500 millibars. So we're going from the surface on up to about the halfway point in the atmosphere. And then for the x-axis, we have temperature in degrees Celsius here along the top. And down here on the bottom is Fahrenheit. We'll use 10 degrees Celsius. Basically, what we're doing is we're starting with this original layer of air. And again, this is of the atmosphere, the surrounding atmosphere. We're not talking about the air parcel at this point. We're just talking about a layer of the atmosphere from 600 millibars It goes up to 500 millibars. Notice that the temperature is decreasing as we go from 600 to 500. So the temperature is decreasing with height. Now the temperature of this top portion of the layer is obviously it is less than the temperature of this bottom portion of the layer. And notice that the top portion of the layer, if we begin to take this layer and we move it down to the surface, notice that the top portion of the layer will have to go further down. And so we begin to basically warm it. Recall that as air moves down, as the air begins to move down, it compresses, the molecular speed begins to increase, and therefore we increase temperatures. So what ends up happening, this layer begins to move down and it warms, and eventually it reaches down near the surface at about 900 millibars. And so the top portion of the layer, since it has further to go than the bottom portion of this layer, will warm more than the bottom portion. Now the bottom portion, we see, starts out right about minus 21, and eventually it warms to about 16, 17 degrees. But the top portion of this layer is at about 20 degrees, right at 20 degrees Celsius. And so now we've taken an initial layer where temperature was decreasing with height, and we move it to the surface, and the layer is now increasing with height. This is considered a very stable type of situation. And so this produces basically what we term a temperature inversion, where we have warm air sitting over cooler air. And we talked about this earlier. If I go back, notice that we have warm air. We're looking at the nighttime profile of sand. And we have warmer air here compared to here. It's cooler. And so we said this was a stable condition. So if we take a layer of the atmosphere and we move it down, we warm it with compressional heating, then we create a very stable type of situation. So if an air parcel tries to rise from the surface, it will be cooler than the surrounding air, and so therefore it will begin to sink down. And we can see this. Let me clear this out. It's a very important concept. This is the change in temperature increasing of the atmosphere. If we take a temperature of an air parcel, we start it right here. We know that if the parcel is dry, it will decrease at 10 degrees Celsius per kilometer. And so the temperature of the air parcel will decrease. And so the temperature of the air parcel here is less than the surrounding atmosphere, and so it will want to sink back down. So this is considered a very stable situation when the environmental lapse rate, the change in temperature of the surrounding atmosphere, is less than the change in temperature of either the dry adiabatic lapse rate or in this case the moist adiabatic lapse rate. This is what we would term a subsidence inversion, and it typically occurs when you have high pressure moving over your area. Now let's look at a case of an absolutely unstable atmosphere. An absolutely unstable atmosphere is one where there can be a lot of cloud buildup, a lot of convection, thunderstorms, things like this. And basically an absolutely unstable condition means that if we were to lift a parcel of air up into the atmosphere, whether it's dry or moist, will be warmer than the surrounding air. And so therefore it will continue to rise. For instance, let's look at this helicopter example where we have this helicopter attached to a piece of air. And then we look at the temperature of the surrounding air, which is 30. You see right here, temperature of environment. And this is the temperature of the air parcel. And so as this air parcel begins to rise, it goes 1 kilometer up. It decreases at the dry adiabatic lapse rate, which is 10 degrees Celsius per kilometer. Again, that's how the temperature decreases. So the temperature of the air parcel is 20. The temperature of the surrounding atmosphere is 19. The air parcel is now warmer than the surrounding air. And so therefore, with it being warmer, less dense, it's more buoyant and will continue to rise. And so it rises up another 1,000 meters or another kilometer up to 2 kilometers. And now the temperature has gone from 20 down to 10. So it's went from 1 kilometer to 2 kilometer. It decreases another 10 degrees Celsius. And so the temperature of the air parcel at 2 kilometers is 10. The temperature of the surrounding atmosphere is 8. And so the parcel is still warmer and will continue to rise. And in fact will continue to rise until eventually it condenses and forms a cloud. Now, if this air parcel was decreasing at the moist adiabatic lapse rate, it would do the same thing. In other words, if it was the moist adiabatic lapse rate, the change in temperature would be 6 degrees Celsius per 1 kilometer. And let's just use an example here. And let's just say that this parcel was saturated. And as it went up 1 kilometer, what would be the temperature of the air parcel now? Instead of 20, since it's moist, it would be 24, because it changes at 6 degrees Celsius per kilometer on average. Notice that it's warmer than the surrounding atmosphere of 19, so it would continue to rise. Here from 24, it would be 18, and so now the temperature of the air parcel is 10 degrees warmer than the surrounding atmosphere, so it would continue to rise. And you'll typically find these types of conditions on hot, sunny days, where it's very warm at the surface. Now, this part of the example, we use the helicopter example, but again, if we look here, this dashed line is the dry adiabatic rate. It changes at 10 degrees Celsius per kilometer. So if it starts off at 30, the air parcel at 1 kilometer would be 20 degrees, you see right here, at 1 kilometer. The atmosphere, let me clear this off here a second. The temperature of the atmosphere, which is represented by this solid gray line, is how the temperature of the atmosphere. In this particular example, the environmental lapse rate, or the change in the surrounding air, is 11 degrees Celsius per kilometer. So it starts off at 30, and at 1 kilometer, we see the temperature is 19 of the surrounding air. And we see that here. Now we have another type of stability condition called conditionally unstable. Recall from the previous slide, we have an absolutely unstable atmosphere. In other words, that air parcel will continue to rise. But we have something called conditionally unstable. And just what it says, it's based upon the condition of the atmosphere. And the way this is set up is if you have a situation where the dry adiabatic lapse rate, in other words, the change in temperature of the dry air parcel, is greater than the change of the surrounding air, the environmental lapse rate, which is greater than the moist adiabatic lapse rate. If you have this condition, then we have what we consider a conditionally unstable atmosphere. In other words, conditions are initially stable. Okay, in other words, they're initially stable when the environmental lapse rate, that's the change in temperature of the surrounding atmosphere, is somewhere between the dry and the moist adiabatic lapse rate. Now keep in mind, when we're talking about dry and moist adiabatic lapse rate, we're talking about the temperature change of the air parcel. Now if the air parcel is unsaturated, if it's considered dry, it will change at the rate of 10 degrees Celsius per kilometer at the dry adiabatic lapse rate. If the parcel is moist, in other words, if we've already had a cloud form, then the change in temperature of the air parcel is by the moist adiabatic lapse rate. So air that is dry is always cooler than the surrounding atmosphere and will begin to sink. Let's take a look at that. So we're saying that if the air parcel initially that we have moving up through the atmosphere, if it's dry, it will be cooler than the surrounding atmosphere in a conditionally unstable atmosphere, and so it will want to sink. And let me show you how that works. So we look over here. Again, we've got the helicopter example. We've got the dry air decreasing at 10 degrees Celsius per kilometer. It goes from 30 to 20 to 10. Now the change in temperature of the atmosphere, it changes at the rate of 7 degrees per kilometer. It goes from 30 to 23. So in this example, the environmental lapse rate is 7 degrees Celsius per 1 kilometer. Okay, that's the environmental lapse rate. The dry adiabatic lapse rate, if the air parcel is dry, is 10 degrees Celsius per 1 kilometer. And so if the change in temperature of the air parcel is greater than the environmental lapse rate, in other words, if it's cooler, if it goes from 30 to 20 in this example, and if you compare that with the surrounding air, which is at about 20 and 23, then this air parcel is going to want to sink back down toward the surface because it is cooler than the surrounding atmosphere. Now, if we look over here and let's just say the parcel is saturated, this same parcel that begins at 30 degrees Celsius, and notice the environmental lapse rate is still 7 degrees Celsius per kilometer. Now the moist adiabatic lapse rate is 6 degrees Celsius per 1 kilometer. So the environmental lapse rate, in other words, the change in temperature of the surrounding atmosphere, is greater than the moist adiabatic lapse rate. So if we look here, the temperature of the environment goes from 30 to 23 over the first kilometer, and the temperature of the air parcel, which is saturated, goes from 30 to 24. So the air parcel now is warmer than the surrounding atmosphere. It will continue to rise. At 2 kilometers, it's 18, and the surrounding atmosphere is 16. It's still warmer, so it will continue to rise. It's 12 at 3 and 9 with the surrounding atmosphere. So in this case, the atmosphere is considered unstable if the air parcel is, if the adiabatic change of the moist air parcel is less than the change of the environmental lapse rate. So if the parcel is saturated and the environmental lapse rate, in other words, the temperature change of the environment, is greater than what we would see of the air parcel, the moist air parcel, then it's considered unstable and will continue to rise and eventually form a cloud. Now, the types of clouds that can be produced in a conditionally unstable atmosphere. Now, if your air parcel is dry, remember we talked about the air parcel would move back down to the surface, and so you'd have no clouds. So you'd have basically clear skies. However, if it's a moist parcel, and we saw from the previous example that if it's moist, it will continue to rise. And so then you would have Cumulus castellanus, these types of clouds, cumulus clouds that look like castles, and eventually some of these would form into cumulonimbus clouds, or thunderstorms. You see the rain right there underneath this particular one, and the anvil top. So your atmosphere is unstable based upon the condition of the air parcel, whether it's dry or whether it's moist. Well, we've learned about the different cases of instability. Absolutely stable, absolutely unstable, conditionally unstable. But what causes instability? What mechanisms cause the atmosphere to become more unstable? What causes air to rise so that eventually clouds can form? Well, to look at this, basically unstable air normally needs a trigger. In other words, it needs something to start the air moving upward. And in this particular case, as the environmental lapse rate steepens, in other words, as the temperature of the surrounding atmosphere begins to decrease more rapidly than the temperature of the air parcel, it becomes unstable. In other words, the temperature of the environment might decrease like this. The temperature of the air parcel decreases something like this, where we have temperature increasing this way. The levels of the atmosphere as we go from 0 kilometers to 1 kilometer, 2 kilometers, and so on. So we see at 1 kilometer here, the temperature of the air parcel is actually warmer than the surrounding air at that particular level, and so the air parcel would continue to rise. Another way that we can do this is we can heat the air below. In other words, let me go ahead and clear this. Let's say we have this same type of setup, temperature increasing from left to right, and the height of the atmosphere increasing from 0 up to, let's say, 3 kilometers. And let's say in the morning we have a temperature profile that looks something like this. We saw this in RadSim. But if we warm, as soon as the sun comes out and we warm the temperature at the surface, we begin to see a temperature profile that looks more like this. In other words, temperature begins to warm at the surface, and now we have a temperature increasing or decreasing with height. So if we heat the surface, we can steepen this environmental lapse rate, the way temperature changes with height. Or we cool the air aloft. So let me go ahead and erase this. And you really should spend some time, especially with this slide, trying to figure out what is going on here. This is very critical to your understanding of stability. Like I said, we can take initially, let's say we have air doing something like this, and this is the environmental lapse rate. So we see temperature increasing as we go, or decreasing as we go from the surface, and then begin to increase. Well, if we begin to bring cooler air aloft up here, in other words, we change this temperature profile to look something like this, where temperature is decreasing rapidly, then that becomes a very unstable type of situation. So again, the causes of instability, day versus night. This is a very unstable situation where we have temperature decreasing with height during the day. So we have warm air at the surface, cool air aloft. That's an unstable type of environment. At night, however, we have cooler air here at the surface and warmer air aloft. That's a very stable condition. So this would be considered a stable profile. And during the day, temperature decreasing rapidly with height, we would consider this an unstable type of profile. Another way that we can trigger instability is mix the air. Notice that this is the environmental lapse rate, temperature changing with height, before we mix the air. As we bring some of the warmer air from aloft, or actually we bring some of the cooler air, we begin to bring it down, and it begins to warm by compression. Remember, we take air and we move it down in the atmosphere. It begins to compress. It has work done on it by the atmosphere and begins to heat. And so then what we begin to do is we begin to take the temperature of the surface here and increase it. And so then we take some of the air at the surface, we begin to move it up, the air begins to cool, and so we begin to see the air cooling from A to B. And so now we have a very unstable type of sounding here by simply mixing air. Again, the whole idea is to steepen the lapse rate. In other words, make sure that the change in temperature with height is pretty dramatic. Temperature decreasing with height. Now, another way that we can cause instability, earlier we talked about taking a layer of air aloft and moving it down. This would create a very stable type of environment. Now we're going to do the opposite. We're going to start with a layer in the atmosphere, right at the surface, and just above the surface. And now what we're going to do is we're going to cool the air. So initially we've got an isothermal profile here. In other words, temperature not changing with height. It's pretty steady. And I'll show you this. Let me erase the ink. Here at the surface the temperature is about, it looks at about 13. If we go up to 900 millibars, the temperature is 13 because it's still right at 13. And so we have a very, basically a very stable profile. Now if we take this layer of air and we begin to lift it up in the atmosphere, we begin to lift it, and what will happen is that this part of the atmosphere, or this top layer here, has further to go. And so it cools at a rate of about 10 degrees Celsius per kilometer. And so it will cool faster, this top layer, than the bottom layer. And so what will end up happening as we lift this layer up, the top layer is now cooler. In other words, it's at about minus 35. And the bottom portion of this layer is at about minus 31. So now we've got this layer being decreasing with height, the temperature. And so what we've done is we've taken an isothermal, in other words, temperature not changing at all, and now raising it up in the atmosphere, where the temperature is now decreasing with height. Now I understand this is a very difficult type of concept to understand, and probably something we'll spend a little time in class after you've had a chance to review this lecture. Yet one other way of causing instability, and this is what we call convective instability. Now again, we have layers here in the atmosphere, but the bottom layer is saturated. Okay, so it's going to change at the moist adiabatic lapse rate, which is 6 degrees Celsius per kilometer. Again, this is how temperature changes. It decreases 6 degrees Celsius per every kilometer in height. So if we take this at 1,000 and we move it up to 2,000 meters, we initially start off with a temperature of looks right about 9.5, 10 degrees. And so if this bottom layer here is saturated, at this point here, it changes from 9 to about, or actually from about 10 to 4. So we take this bottom layer here, and since it is saturated, we raise it up in the atmosphere. It cools at 6 degrees Celsius per kilometer. The original layer, the top portion here, is considered unsaturated, and so it will cool at the dry adiabatic lapse rate. And so what we have basically is overturning of the atmosphere here, whereas this one goes from about, it looks like about 12 to about 2 degrees as it goes up into the atmosphere. I'm sorry, it goes from 1450 to 2450, which would be about 2 to 3 degrees. And so it decreases 10 degrees Celsius per kilometer. And so the situation here is that we have the top portion of this layer dry, the bottom portion moist, and so we have moist air at the surface, we have dry air aloft, and we take this and we begin to lift it. We lift it with a front, we lift it with a cold front, a warm front, or we lift it with over a mountain. And what ends up happening is that now the top layer is quite a bit cooler than the bottom layer. Here we had temperature increasing with height. We took this layer, we raised it up, and now we have a very steep lapse rate where temperature is decreasing with height rapidly. This type of profile will produce severe thunderstorms, tornadoes, areas, things like that. So this particular slide here is just a summary. This is at the at one of the ends of the section in your textbook, and I would just encourage you to pause here for a few minutes and just take a look at the summary and make sure you understand what is going on here. Okay, we'll spend the last few minutes of this particular module looking at the development of clouds. We already know that most clouds form as air rises and cools to the dew point. We saw that in mountain sim. And some of the following mechanisms are responsible for the majority of clouds that we see. The first one, and we talked about this early on, I think this was back in, may have been even chapter 2, we started talking about convection, basically heating the air at the surface. And as the air begins to warm, it begins to rise. Eventually, it hits the saturation vapor pressure curve, as we saw in mountain sim. And this would be the base of the cloud, something we call the lifted condensation level. We'll talk about that here more in a moment. But as long as the air parcels within the cloud are warmer than the surrounding air, the cloud will continue to develop until eventually it reaches a point of where it's very stable. And then you begin to have some downward air on the side of the mountain, or I'm sorry, on the side of the clouds. And this is what you would typically see in a summer afternoon, where you see these nice puffy cumulus clouds and areas of blue sky in beneath. Recall that as we begin to have air moving downward, it compresses, it heats. In other words, it moves away from that saturation vapor pressure curve, and so the air is dry in between these areas of upward moving air, followed by downward moving air to the side. So this would be caused by surface heating and basically free convection. The next one, which was mountain sim, is we took air, we moved it up the mountain, we forced it to rise, Eventually it cooled to the saturation vapor pressure curve, condensed, formed a cloud, and again as we continue to lift it, the cloud begins to form upward, and eventually as the air begins to go across the other side of the mountain, it begins to warm, moves away from the saturation vapor pressure curve, and begins to have clear skies. So typically with mountains you have rain on the windward side, and then you have a rain shadow, in other words an absence of rain, on the downward side or on the lee side of a mountain range. Another way, which is what we see over Iowa, is that typically around low pressure we have upward moving air. With low pressure we typically have lower pressure here, and to fill in that area of lower pressure we have air coming in from the side. The air converges, it meets, and it can't go into the ground, so it has to go up. So around low pressure we have upward moving air, and so as air begins to move up, it begins to cool, and eventually it reaches the saturation point, the saturation vapor pressure curve. We have condensation, and as you will learn in the next chapter, some of these processes produces precipitation. So we've talked about free convection, warm sunny days, moving air up over a mountain, we call orographic lifting, or upward moving area of air near low pressures. And recall that winds around low pressure are counterclockwise and inward. The air begins to converge. And converging air will begin to rise and cool and form a cloud. Another way we can do this is through a front. Notice that we have a cold front. The cold front is moving this way. We have cold air back this way, and we have warm air coming in this direction, and so the air begins to rise along both a cold front and along a warm front. So anytime we have air rising, it begins to cool and eventually will condense and form a cloud. In this particular case, a thunderstorm. So again, a cold front or a warm front acts to lift the air, and that's what produces clouds and eventually precipitation. Now let's just talk briefly about surface heating and free convection, and I've kind of touched on a bit of this already. But again, during the day we begin to have air that's being unevenly heated at the Earth's surface, and as the air begins to heat, it rises, it cools, and eventually condenses, forms a cloud. And if the air is still unstable enough, the cloud will continue to develop right here at this point. So this is a blob of warm air here, and as it begins to move upward, it reaches the saturation vapor pressure curve, and at this point we have condensation and a cloud forming here. Notice also that we have air moving out to replace the rising air, so we have air beginning to move downward, and it begins to warm as it moves downward. And a lot of times you'll see these types of clouds, cumulus clouds, and then areas of downward moving air, which would represent clear skies. So we have upward moving air producing clouds, downward air producing areas of clear skies. Now, we won't spend a lot of time on this because we've already talked about this, but basically you've got temperature versus height in this graph here on the left, and then you have the rising bubble of air here, and then you have a temperature profile of the air parcel, the temperature as it cools dry adiabatically, and then the change in dew point, and then we have relative humidity increasing to 100% and then staying at 100%. So basically what we have here is, let's go to this blob of air. Warm surface air at 35 Celsius begins to rise and begins to cool. And eventually, now this right here is the environmental temperature, the air surrounding the warm blob of air. And so it is rising, and at about, as it goes up to a half of a kilometer, it decreases by 5 degrees. And so we see the height here, 1,000 meters, but at this point it's at about 500 meters. for about a half a kilometer. And since the air is considered unsaturated, we haven't formed a cloud yet, so it's unsaturated, it cools at the rate at 10 degrees Celsius per kilometer. And so since it's gone up a half a kilometer, the temperature of the blob of air is 30. The temperature of the surrounding air is 29, and so the environmental lapse rate here is 6 degrees as we go from here to here. And here it changes to 5, and here to 3, here to 2, and then it begins to warm again. So the environmental lapse rate, you see temperature decreasing with height. At a certain point, it doesn't change as rapidly, and then it actually begins to warm. So we see how the temperature of the surrounding atmosphere changes with height. And so as long as this environmental lapse rate is decreasing with height, it's very steep, we should begin to see air to continue to rise. We're talking about a very unstable air mass. But once it begins to increase, temperature begins to increase with height, this is what we call absolutely stable, or a subsidence inversion. So we have this blob of air continuing to rise. At 1 kilometer it's 25, the surrounding air is 24, it's still warmer, so eventually it cools to the condensation point. Okay, and so a cloud begins to form. The air continues to move up. It's decreasing now. Since a cloud is formed, it's now decreasing at the moist adiabatic lapse rate. In other words, 6 degrees Celsius per kilometer. So as we go from 1 kilometer here up to 2 kilometers, the temperature of the air parcel, the moist air parcel, goes from 25 to 19. At this point here, it's the same temperature as the surrounding air. And so since it's the same temperature, it will no longer rise or fall. It will stay right here. So this is the top of the cloud. So in this type of temperature profile, we would have a case where we would have cumulus clouds forming, but not any further into a thunderstorm because it's stable at this point. Temperature's increasing with height. We get a little bit closer. Again, we can see that this portion here is considered unstable because temperature is decreasing with height. And at this point, it's become stable, and so the cloud itself can't develop very high. So basically, the environmental lapse rate determines the stability. Now, as we go through the day, the temperature at the surface begins to increase, and so now your temperature profile of the atmosphere may look something like this. And so now you have a very unstable atmosphere here at the surface. Play around with this a little bit and see what you come up with. Again, this is something we'll cover in class. Now, as we go in this particular one right here, let's say that this portion of the atmosphere is conditionally unstable. If you recall when we talked earlier about this, if the parcel is moist, if it's saturated, then the air parcel will continue to rise. And in this case, since we've already formed a cloud at this level, the change in temperature of the air parcel is now at the moist adiabatic lapse rate, so it will continue to grow. However, at about this point, the temperature of the surrounding atmosphere is not changing, and in fact is increasing right here, so the cloud cannot develop any higher than here. With this type of setup, we would get cumulus congestus types of clouds. And finally, if we have this type of setup where a very deep layer of the atmosphere is conditionally unstable, we will get a thunderstorm forming, assuming we have sufficient moisture. Again, conditionally unstable means if your air parcel is moist, and so the temperature is decreasing at the moist adiabatic lapse rate of about 6 degrees Celsius per kilometer, it's considered an unstable atmosphere. And so the thunderstorm will continue to develop. And you'd have something like this, where you'd have a cumulonimbus, a thunderstorm cloud here, one back here. On this particular, again, we have orographic lifting where we have air moving up. The initial air temperature was 20, the dew point was 12. At this point here, once we reach the saturation vapor pressure curve, temperature and dew point are the same. And since this air parcel is now considered moist, it will decrease at about 6 degrees Celsius per kilometer. So as it goes up another kilometer, the temperature and dew point is 4. We go up another kilometer, it drops by another 6 degrees. It's now -2. Now, as we move to the other side of the mountain, notice, however, that we've actually taken all of the condensation out of the air parcel. Now it begins to warm. And so now we have a dry air parcel. So as the air parcel is going down the other side of the mountain, it goes from -2 at 3 kilometers to 8 degrees Celsius at 2 kilometers. So it's increased by 10 degrees Celsius per kilometer. Notice the dew point now is 0 degrees Celsius. We take the temperature as it goes down another 1 kilometer, it increases to 18, and so the air is warming rapidly as we go down the mountain. And now the air, that same air parcel, has a different temperature of 28 on the lee side compared to 20 when it started on the windward side. Also notice the dew point temperature, an indication of moisture. We've taken a lot of moisture out of that air parcel by raining the precip out. And so the dew point is quite a bit lower than it originally was on the other side of the mountain. This is a pretty neat type of cloud. It's called a mountain wave cloud, or a lenticularis, and it's typically formed as air moves over a mountain range. So we have rising air here, begins to form this type of lens-shaped cloud, and as the air begins to sink, it begins to dry out, and as it begins to rise again, we begin to get, again, these types of lens-shaped clouds. I used to see these when I was at the University of Kansas. We'd have air coming off the Rockies over in Colorado, and sometimes you'd see these spectacular lenticularis clouds, named because they look like a lens.